Okay, good morning everyone. So today we will continue our lecture on linear regression analysis. Last week we just discussed about the result of your mid-exam. This week we will continue with our plan for the lecture. So I think, if I'm not mistaken, the last thing that we learned before the mid-exam is about the using the model for estimation and prediction and some of other linear models, right? So then now we will continue to the test for comparing nested models. But before that, maybe it's good to have a look a little bit at some other linear models. Okay, so then we look at we will be referring to Mendenhall book. Let me see. Okay, so second course in statistics by Mendenhall and Sinchich, and then we will go to the chapter 4. That is, maybe we will just start with we've done the interaction model, right? So we will start with the second order model. We've learned it a bit before, the work from home and study at home time period, but it's all right. We can just have a look at this thing again just to fresh your mind about this. Okay, so the quadratic model is the one that's taking the quadratic term in it. Okay, and as we have learned in very early class of linear regression, that this model, although it contains the quadratic term, it is still considered as a linear model. Maybe you could just recall again what's the definition of our linear regression model. Okay, so then it depends on the sign of this beta 2. Then the quadratic model can be concave upward or concave downward. Okay, this is the form of the model, and then I think that we will just go straight to the example. Okay, so this is the example of data on immunity, okay, and fitness level of 30 subjects measured by the, what is IgG? IgG is that immunoglobulin in blood, indicator of a long-term immunity. Okay, and then the maximal oxygen intake, okay, or uptake. Okay, we will try to model the relationship between these two variables, IgG and maximal oxygen uptake, where the IgG becomes the response variable and the oxygen uptake as the predictor variables. Okay, in this book, in Mendenhall book, if I'm not mistaken, it's using SPSS. Okay, SPSS or SAS. Okay, so we will SPSS Minitab, but now we will try to use the R. So then before this, I already input the data to save time. So this is the data that we have according to that table. So then this is the IgG level, and this is the oxygen uptake for those 30 subjects. And then let's make a data set of it. Let's say data 4.2, because we take it from table 4.2 of Mendenhall and Sinchich book in page 202. So then I will put this as data frame. The first variable is that IgG, the second variable is that oxygen. Okay, so then this is just to have a look at the data 4.2. Okay, so here is our data. Okay, this is how it looks like. Okay, if you want to look at other properties of the data, you can just type dim of data 4.2, it gives you the dimension of the data, and it gives you like 30 and 2. The first dimension is 30, is the number of observation. 2, the second dimension is 2, that's the number of variables that you have in your data. And then if you want to know what variables are there, of course in here, because we already viewed it, you know what they are, but just in case later you have lots of variables, and then it's kind of like, the screen is so full with the columns of the variables, then you can just always type something like this. So I'll just copy, and then, okay, so we have that types, oh, not types, sorry, the names, and then it will give you the names of the variable. And then if you want to know the types, okay, you can't have types for data frame, but you can have types for variables, for example like this. And then, oh, could not function, okay, something like this. Okay, so oh, it's not type, I forgot it, it should be like class. Okay, so we know that this is of numeric type. Remember that we learned about the type of variables or the scale of variables, that's either nominal, ordinal, interval, or what is it, ratio. So this is how we get to know what is the type of our data. Okay, now what do we do with this data? Okay, the aim is that we want to model the relationship between the oxygen uptake level with the IgG through the regression equation. So then, again, first thing to do before you put in the regression is always do visualization of your data. So then let's try to put the visualization of the oxygen and that IgG. And we have something like this. Okay. So, what do you think about the relationship of these two variables? Do you think that it forms like a linear trend? Looks like it. So, we have kind of like, okay, this is a really good linear line, but if you what is it? If you look carefully, it's a kind of a bit bending around here, so probably we can just put it like, a little bit curvature. Okay, so we'll try both, but again, if you are what is it, curious about, for example, the correlation, then we have that the correlation is 0.95 between the oxygen uptake and the IgG level. So yeah, as can be seen from this graph, there's really a strong correlation between these two variables. So it seems that performing a linear regression on these variables will give us kind of like a good result. Okay, let's fit our regression. So I'll just put the name as regression 1 because later I will try to do another model. So regression 1 is I will just put, so the IgG as the response, and then the oxygen level as the, what is it? The predictor variable. And then to get the result of this, I will just have the summary of it. Okay, so this is the summary. And how do we tell our story from this result? Okay, so in here we have this result. Okay, firstly, maybe we just need to check whether our model is good or not. This is like testing the whole model, but then you can just look at this one, the coefficient, the p-value for the oxygen, that is 2.86 times 10 to the power of minus 16, which is almost 0. So the p-value is very small, less than 0.001, is close to 0. So then the null hypothesis that beta 1 equals 0 is rejected, which means that beta 1 is not 0, which means that your regression, linear regression is, what is it? Your linear regression is good. So here we have that the regression fit line is that the equation here. So we have, what is it? Because it's the fitted line, so we always, put the hat on it to say that this is just based on one sample. So if we try another sample, then there might be slightly different results. Okay, so that IGG equals that the beta naught hat is -1 or 2.53. I'll just take 2 digits plus the 32.79 of the oxygen level. Okay, so there's our fitted line from this result. And then, okay, so to test the model again, before that we are testing this, and then, okay, so the null hypothesis that the beta 1, okay, so it comes actually from the model that IgG equals beta naught plus beta 1 of the oxygen level plus the epsilon, where the epsilon follows a normally identical, independent and identically distributed with a mean of 0 and the variance of sigma squared. Okay, so from this model, to know whether the model is useful or not, then we just need to test whether the beta 1 equals to 0 or not. So then this is our hypothesis that beta 1, oopsie, that's the null hypothesis. That null hypothesis is that beta 1 equals 0 versus the alternative hypothesis is that beta 1 not equal 0. Oopsie, beta 1 not equal 0. Okay, and then for this hypothesis testing, just to be quick, then we will just need to look at this. Okay, the t-value is 16.974, and then you have to compare this t-value with the t-table with the degrees of freedom. So the, what is it? Decision rule, compare the t-value with t from table with the degrees of freedom. The degrees of freedom is n minus the number of parameters to be estimated, right? And here we have that, that the number of regression parameters, that is beta naught and beta 1. Actually, we estimated 3 parameters, including these, the variance, but then in this case, we only consider the number of regression parameters or the regression coefficients, that is 1 and 2, beta naught and beta 1. So here is -2 and is that 30, so that's why in here you get actually 28 degrees of freedom here. It comes from the sample size of 30 minus 2. Okay, so then you look at that, and then you see the value of the t, but then it's just an instant result. We just need to compare the p-value with the significance level that you picked, for example 0.05, and here we get the decision that we reject the null hypothesis, means that this model is good. How good is the model? Then you look at the r squared, and here we have the r squared of 0.91 14. And the adjusted R squared is 0.9083, which is not really different from the R squared. So we can say that around 90%, or yeah, just round it up to 2 digits, around 91% of the variability in the value of IgG can be explained by the oxygen uptake through this model, which is actually kind of quite good. Okay, so actually we are happy with this model. Okay, however, if we look at this result at the plot, because we suspect there's some kind of, it's not really the straight line, but there's kind of like a little bit curvature here, a little bit kind of like the trend to go down. So we will try to fit an alternative model that probably could be a better fit to this data. And then let's try using your mathematical knowledge that what kind of function that allows for curvature. So we might propose like a quadratic model. Okay, so that's why here we just copy and paste it, and then let's name it regression 2. And now instead of a linear one, then we will need to add the quadratic part of the oxygen. Okay, but before that, of course, then we have to define what is OXG2. That is just the oxygen square. Okay, and then we have this. Okay, and then we try to run this model, and we get the result here. Okay, so what do we need to look for this result? Of course, first one is that whether the model is useful or not. So again, just taking, okay, so the model, I will just copy paste this. Okay, for the second model, so we have that the model is beta 0 plus beta 1 oxygen plus, here is beta 2, oopsie, beta 2 oxygen squared plus epsilon, and the regression fitted line is that minus 1463.01 or 02 plus 88.24 oxygen minus 0.5354, just put it 54, oxygen 2 or oxygen squared. Okay, so that's the fitted line. And then what can we see from this model, from this result? Of course, the first thing to ask is the model useful? And then by looking at the stars here, simply saying that all the coefficients for these variables are significantly different from 0, which means that all these variables are contributing significantly in explaining the IgG. Okay, to say the model is good enough or not, actually it doesn't have to be all the variables to be significant. Just one of them significant is enough, but in this case it's better than that because two variables included in the model, they're both contributing significantly to explain the dependent variables. Okay, so the hypothesis is a little bit different because now we have more than one variable. So in here that instead of, oh, it should be 0 here, sorry. Okay, so instead of having the beta, just beta 1, then we do the model testing for all the parameters straight away. And then the alternative is not beta 1, not equal. It's not that, okay. It's not that something, oopsie. It's not something like that because this means that we expect that both betas to be different from 0. It means that while actually what we mean is that only just one variable is enough to say only one variable or only one coefficient different from 0 is enough to say that the set of the the predictor variable is can be used to explain the response variable. So to be simple, I'll just say otherwise and then use your knowledge from the uh, logic class that the negation of this statement is that not this, which means that it doesn't have to be both 0, which means that can either one be 0 or both be 0 is okay. Okay, so then the decision rule is that no longer t-value, but we have the f-test, and then we compare it with the f-table from with the degrees of freedom. You know, the f-table, f distribution has 2 degrees of freedom, right? Okay, with the f1 and the f2, and then with the f1, the degrees of freedom, the first degree of freedom is the number of the parameters to be tested. That is, we have beta 1 and beta 2 in here, a little bit different with the t-test, and then we have that the second degrees of freedom is that's the one thing the same with this one. So the number of the sample size minus the number of all regression parameters. In this case, we have beta naught, beta 1, beta 2. So there are 3. So here we have sample size of 30. So here we have 30 minus 3, that is 27. Okay, so from this result, actually, you can see that the F value is 203. That is our F value here, 203. And then with the degrees, and we should compare this value with F value from F table with the degrees of freedom 2 and 27. You always can do it online here, for example, like, okay, so if calculator, and then you can have this one, and then the first degree of freedom is 2, the second degree of freedom is 27, and then here it says that cumulative probability is a little bit different how it presented, but then because we want it, let's say we choose the significance level to be 0.5, so here we have that the significance level, that is alpha equals to 0.5, and then we know that F distribution is a positive distribution. Okay, so I'll just use 5, that's the cumulative. The 95%, this is the cumulative probability. So we have here the F value is 3.35. Okay, so the decision rule is that reject the null hypothesis if the calculated F is greater than 3.35. And then what we have here is that the F is 203, way bigger than 3.35. Or actually, to be simple, then you just need to look at the p-value here. You don't have to do all this kind of procedure, but I was explaining it just for you to know how it works. Okay, so in here we can see that okay, the p-value is close to 0, so it means that this hypothesis is rejected, and then we can conclude that our quadratic model is a good fit to the data. How good is it? We can see that the R squared is 93.76 and the adjusted R squared is 93.3. Okay, so just differ by 4%, 93.8. Yeah, just differ by 0.5%, which is not too much, which means that actually adding the quadratic term is okay with the model and it's also significant. So we are happy with this model, okay, with the result. So I think that if we want to choose which result that we want to use, is it the first one or the second one? Again, the decision is that if you want it to be simple, okay, then taking the first one is okay because this the explanation of this model is also good, right? So if you look at the previous result, the R squared is 91%. And then while here, so we get 94%. So by adding this quadratic term, we only have a improvement of 3%. So if you think that 3% is just not too much, so I just choose a simpler one, choose the first model that is just a linear one. That's okay, you can have a go with that one. But if you really think that, oh, okay, additional improvement of 3%, yeah, that's not much. But then if you look at this, there's kind of like really the tendency of a little bit, bending, okay, kind of going up here, but then a little bit, okay, the rate of increasing, this is, the rate of increasing is high. It's kind of steep, but then here is kind of like a little bit, okay, not that steep, okay, so we can say that the rate of increasing is decreased, and then over here again keeps decreasing and then start to like going down. So for that kind of things, of course, that we have to put in like, an appropriate relationship. Okay, what kind of relationship that says like that it increases, but then as the value of this oxygen increases, then the rate of increasing is kind of like getting slower and slower and slower, and it seems that at one time point it starts to decrease. While if you take a linear one, then it will keep increasing. So in that case, if that's your consideration, then we should take the second model, okay? And that's how we interpret this value here, the negative 0.5. The number, the magnitude 0.5 itself, it doesn't have, we can't really say anything about that, but we just look at the sign here. Negative signs means that the downward curvature, and it means that when the X increase, when the oxygen uptake increase, the level of immunoglobulin IgG increases as well, but it increases with the rate, with the slowing level of increase, and then later at some point it will reach its peak, and then the increment of oxygen level will no longer increase the IgG, but that will the IgG level will go down again. Okay, so that's how we interpret the negative sign of the quadratic term in here. What about the number 88? Okay, again, if we say that, okay, remember that in class, I told you about, okay, this is just a symbol, everyone, okay, like this is just your x1, and this is just like your x2, and then we can just say what is the interpretation of beta 1. Okay, I'll just put a highlighter on it. Okay, so what is the interpretation of beta 1? Oh, okay, beta 1 represents the contribution of x1 to the IgG, but for each 1 unit increase, beta 1 is the increase or decrease in IgG for each 1 unit increase in X1 while setting all other predictors to constant. Okay, that's kind of like a template to interpret the parameters here, but now we put it into context. What is our X1 and X2 in this case? So X2 is that X1 itself that is in a quadratic form. So it is impossible to increase X1 by 1 unit, but you keep X2 to a constant. It is impossible. So which means that you can't never do the interpretation of what's the meaning of this 88. Okay, so what we can do here is just that, interpret all these coefficients together. So which means that, okay, in this case, like what we have in class before, okay, so if for example that the oxygen level, if I put the oxygen level equals to such a number, let's say A, then we have this, okay, times A, and then this is times A squared, right? And then if we increase the oxygen level by 1 unit, so to become A plus 1, then in here we also have this A plus 1, and here also we have A plus 1 squared. Okay, and then if we try to open up this, okay, just put it here, then you just need to, okay, just copy everything, okay, and then so we have this is the same here, you have this one, oopsie, and then you have that 88.24, and then here minus 0.54 a squared, right? Okay, and then minus 2 times, a plus 1 squared is a squared plus 2a plus 1, right? So then 2a times times 0.54, and then plus 1 squared times minus 0.54 is that minus 0.54. Okay, and then so you know that the delta difference in that oxygen, not the oxygen, the difference in the let's see. Okay, so the difference in the IgG level due to the increase in the oxygen level is that, okay, 146, this one minus the one up here, so I'll just get rid of it from here. So okay, I'll just copy paste it first so it's clearer. Okay, so this one just subtract it just with this one. Okay, oops, just make it bigger. Where is it? Okay, so then just subtract this minus 4, take it away, and then here 88.248, take it away, and then here minus 54a squared, take it away, and that's what's left for us. Okay, and then so we can have here minus 88.24 minus 2a, we can just put it 2a plus 1 times 54. So that's all what we can say about the interpretation of this result. Okay, so we can't just say, what's the meaning of 88? I don't know. What's the meaning of minus 1463? I don't care, because this is just, the intercept, which sometimes gives you, what is it, something illogical sometimes. And then, so what's the meaning of this 0.53? No meaning except for the sign. That's saying that if it increases, then it increases with the decreasing rate of increment. If it decreases, then it will decrease with the, what is it? Again, what is it? Let's see. Oopsie. Okay. So again, if it increases, it will increase with the decreasing rate of increment. If it decreases, it will decrease with the increasing rate of decrement. Okay. So then, what was it again? Yep. So then, how to do the interpretation about this? We can't do them one by one. We just can do it in something like this. We just can say that, okay, for each unit of change in the oxygen level, for each unit increase in the oxygen level here, because I put A plus 1, then the change in the IgG level, it depends on the value of the initial value of the oxygen level, and then it can increase or decrease depends on that, given by this equation. Okay, so at some point, increasing at the oxygen level uptake will increase the IgG, of course, when this term here is less than 88.24. But then, at some point, increasing the oxygen is no longer increasing the IgG. Instead, the IgG level will start to drop. That is when the value in here is less than 88.24. Okay, so I think that's all that we can say about the quadratic regression line. Okay.